All right, so you're going to find that Gauss's law is at once extremely simple and at the same time very powerful, and yet it's not terribly useful to calculate electric fields. It's not useful unless the charge distribution or the set of charges that you're dealing with has some sort of symmetry that you can leverage. And in that case, it can take an insanely difficult problem like this one and just dispatch it immediately. But it does take that kind of special case. So in this case, we've got two conductors, two spheres, an outer hollow sphere and an inner solid sphere. And the problem's sort of a riddle, or it's sort of a mystery, because it gives you the electric field at a couple of points in space, and it then asks you to calculate what the charge is on the exterior surface of this small inner sphere and on both the interior surface and the exterior surface of the larger sphere. And you're going to see that Gauss's law just takes care of this problem in just a heartbeat. So let's, and in fact you're going to see that you really just have to do one or two calculations here and you'll arrive at the solution very quickly. So let's get the graphic and throw it away so I have a little bit more board room here. And let's start by finding the charge that's on the outer surface of the inner sphere. And I'm gonna call that Q of the outer surface on the inner sphere, Q 0I. All right, so Gauss's, so what one does, the situation we have then is if this is the inner sphere, it's got charges on its exterior, and we can tell that they're negative charges. We can tell that because if we go out here 8 centimeters, I'm going to turn that into meters very quickly, 0.8 meters, that we've got an electric field, first of all, pointing inward. That means the negative charges are here, because fields always point from positive to negative regions of space, and that field is got a magnitude of 15,000 newtons per coulomb. Oh great, what do we do with that? And what we do is we create our own Gaussian surface, and it's very important that that Gaussian surface first and foremost be a sphere. And I say, and you'll see why it's important in just a second. It's a sphere, and it goes through this point. All right, so Gauss's law says, it says that the total flux of electric field that's going across that Gaussian surface is just equal to, I'm going to say it's E dot A. Okay, it's, I guess I don't like that that notation so much, but it is at every point on the surface, the electric field dot multiplied into the normal to the surface. So by virtue of using a cylindrical surface with a radially symmetric electric field, every place that you see E dot dA, what you really have is just EA. And to finish off Gauss's law says that that's equal to the charge inside, and the only charge inside this sphere is the charge residing on the outside of this actual conductor, and it's OI. And the constant of proportionality is the permittivity of free space. Okay, so we're just about done because the area, the total area of this sphere is 4 pi r squared when r is evaluated at 0.08 meters. All right, so we can find Q sub I0 in just a heartbeat. Here we go. Q sub, 0I is equal to, going to move the permittivity of free space up here. It's E and it's A. And I'll leave it like this, r squared for the case where, in this case, r is equal to 0.08. So let's put the numbers in very quickly and we'll get Q0I is equal to 8.85 10 to the minus 12. I'm going to say I always forget the units, or the way the units go on this. We want to end up with charges here. So this is Coulomb squared all over Newton meter squared, times E, which is 15,000 newtons per Coulomb, times 4 pi, times 0.08 quantity squared meters squared. Okay, so if we look at those units, meters squared go away, newtons go away, one of the two coulombs go away. It's exactly what we want, and if we do this calculation, you get Q0I, I think it's 1.07 times 10 to the minus 8 coulombs, and that's about 0.1 nanocoulomb. And let's remember that it's minus, and in fact, the mathematics tells us that it's minus. We don't really have to, the mathematics would have just handed that answer to us, because the flux is E dot dA. So you've got an E vector pointing radially inward, and A vector pointing radially outward. When you dot them, that minus sign shows up. All right, so there's problem one. Problem two said, now knowing this, what is the charge on the inner surface? So in that case, if I could just make a quick little drawing here, if this is the inner surface, I'll just draw a little section of the hollow sphere. Let's go ahead and draw and create a Gaussian surface right in its interior. Okay? The Gaussian surface that we just drawn is spherical. It takes advantage of the fact that the electric field is radial, and it takes advantage of the fact that since this outer sphere is a conductor, that the charge will either be on the inside or the outside. Okay, and in this case, it does a little bit more, because we happen to know what the electric field is on that Gaussian surface. It's zero. It's zero because, again, the charge on the conductor is only on the surfaces. So if E is zero, the flux is zero, and that says that the total charge enclosed in this particular Gaussian surface is zero. It says that the total charge enclosed, it is zero. Okay, and the total charge enclosed comprises the charge that's on the inner sphere and the charge that's on the inner surface of the outer sphere. All right. So this charge, which we just calculated as 0.1 nanocoulomb, has got to be equivalent to the charge that's on the interior surface of the on the outer sphere. So there, we've got not only this answer, but here comes the second answer very quickly, that the charge on the inner surface of the outer sphere is also 0.1 nanocoulomb. It's positive, whereas the charge down here is negative. So we're just about ready to finish this problem. This third problem says, let's move out here to R equals 17 centimeters, 0.17 meters. Let's do the same thing that we've done before. Let's draw yet another concentric Gaussian surface, a surface that's concentric with every other sphere and every other Gaussian surface here. Let's make use of Gauss's law, which says the flux through the sphere is equal to the total charge enclosed. We've already seen that there's charge on the interior, on the exterior surface of the inner surface. There's charge on the inner surface of the external surface. Those two charges cancel, but there is charge on the outer surface as well too. Okay, and that charge has got to obey the Gauss's law. And you'll see the exact same calculation. In fact, let me write it down. The outer surface of the outer sphere is, I'm just going to put the numbers down now and not carry along the units. We've done this enough. 8.85 10 to the minus 12 times 15 times 4 pi times, now in this case, instead of 0.08, we're out at 0.17 squared. All right, so this number is the same thing as this number. Q0, 0 is the same thing as this number, only I've got to multiply it by the factor 0.17 all over 0.08, almost a factor of 4 when you square it. And when you do that calculation, you find that this is 0.48 positive nanocoulombs. Okay, so again, fairly difficult problem, but you treat it very quickly with Gauss's law, primarily because you choose the proper Gaussian surface given the symmetry of the fields. All right, very good.